So we'll start the connection between the eigenvalues and eigenvectors with differential equations. Eigenvectors and eigenvalues come after vector spaces. I can talk about scary things like ghosts, so various scary things, but you are not scared. But when it comes to vector spaces, right? When I say that word, you are scared, right? Vector spaces is something that throws you away. But let's see it in a simpler way. Now, first, let's look at the matrix representation of vectors. This is something you are really familiar with. So, if we take I plus j, for example, you can write it like this in matrix form. You can write it as a column vector, where you can arrange these coefficients in the same order. Right here, they are 1 and 1. Here it is 1, 3, and minus 1. So there are 3 components. So you can arrange those 3 components like this. So the number of components will tell you where you are in. Like here, there are 2 components. That means you are in 2-dimensional space. Here there are 3 components. You are in 3-dimensional space. So why do you need this matrix notation at the first place? I mean, you are very comfortable with this arrangement, the algebraic way of representing vectors. So why do you need this one? Just to put you in trouble? So what's the reason for that? Reason is this. Let's take this example. Consider a robot arm like this part, for example, right? Say this can move only in a certain plane, like this. So if you take this angle, I'll take it as theta 1. This arm, let that makes an angle theta 2 with the vertical direction, this theta 3. So say this in motion. So if you want to describe the motion of this arm, you can do it like this. You can first explain the orientation, the way it is set, the way it is, the arrangement of these arms at a given time instant. Since it is in motion, right, you have to explain, you have to tell something about their angular velocities, like theta dot, theta double, theta 1 dot, theta 2 dot, as well as theta 3 dot. So if you want to configure this, configure means like if you want to mechanically explain its orientation, that's kind of, it's a little crude way of explaining what it is, right? That's called the configuration space thing. So if you want to configure this, you have to explain theta 1, you have to give the values of theta 1, theta 2, theta 3, as well as theta 1 dot, theta 2 dot, and theta 3 dot, right? This motion will give you theta 1 dot, theta 2 dot, theta 3 dot. So how do you, now there are 6 parameters. So how do you explain this? So you can arrange a vector like this. Now look, there are 3 components in the vector. So it is, in fact, even though this moves in R2 in a plane, there are 3 objects here, 3 arms, but still you have to configure it in 6-dimensional space. Sometimes if you take an aircraft or a rocket, for example, you have to explain it, its configuration space may be a 12-dimensional space, so sometimes 24-dimensional space. So here it's from 6D. Now, if you want to explain something like this using ijk, how would you do that? You simply cannot. Because using ij and k, you can go up to 3-dimensional space. So if you want to configure something like this, some system like this, that representation will fail. So that's why there are limitations, but it's sometimes good. Like if you want to play with geometry, this is okay, this is good. However, when it comes to, when you deal with more complicated systems, this representation will fail. But this works fine, right? Because you can simply add numbers to the tail to change it to bring it from one space to another space. Like here, this is a vector in 6-dimensional space. Very simple thing. You can add 2 vectors, right? Like this, for example, if you have, say, this V1, it's a 4-dimensional a vector from 4-dimensional space. Say this V2. If you want to find, for example, V1 and V2, V1 plus V2, you simply add. Using very basic operations you have learnt probably when you were in your O levels. How would you do that? You simply add the corresponding numbers. You don't have to learn it like rocket science. Like you don't need like very complicated stuff from vector spaces. If you have something like that, once you represent it like this, you can simply add them using matrix addition. Because you simply transform, you use matrices to represent vectors. Now all the matrix algebra can be used to operate them, like manipulate them. For example, if you want to add these two, you add them. 1 plus 0, 1. 2 plus 3, 5. 1 plus 0, 1. 4 plus 4, 8. So that's the sum of those two vectors. Simple. So if you want to find the scalar multiplication, for example, say, for example, 3V1 is what? What is V1? V1 is 1, 2, 1, 4. Use your knowledge in matrix algebra. Simple stuff, right? Multiplication by a scalar. So you multiply 3, 6, 3, 12. 3, 6, 3, 12. That's it. So those are the only operations you can do with vectors. That's all. So you don't need vector like 10 statements from vector spaces. This is all what you know. You need to know, right? You convert these once you convert the vectors, like once you represent them as matrices, right? You can add them. You can multiply them by a scalar. In vectors, that's all what you do. Probably you can take dot product. You can do it like using vector multiplication. But here we don't need that, right? That's all what you use in algebra. You convert them into matrix form. Then use matrix algebra which you have learnt in your O levels. That's all. Even you don't have to use matrix multiplication. You simply add them and multiply by a scalar. That's all. That's all what you can do. So you don't need those 10 statements in the definition of vector spaces. This is all what you know. You need to know. Okay. So one reason, right? You should know why you use this notation. Why? Because you can simply extend that to a high dimensional space, or spaces. This one example. And in this case, this is how you do algebra. This is how you add vectors. This is how you multiply it by a scalar. This go hand in hand in R2 and R3 with geometrically you can explain this one. If you write them in IJK, again you add it in the same way, right? For example, if you have I plus j and I plus 2j, you add components of I together, components of j together. Simple thing. Corresponding numbers are added. Same thing. But you cannot add a vector in 4-dimensional space with the vector in 3-dimensional space. But here you can, because both go hand in hand, because they are from the same same family, same space. Simple, right? Now we'll move to next one. Linear transformations. Now that's also something which throws you away, right? But we will see what it is. Let's take this vector. And once it is transformed like this. Excuse me, right? Now, what does this mean? This means this is a vector in R3, as I explained you. There are 3 components, but this vector has 2 components. So it takes a vector in R3 into a vector in R2. Linear means like it should go hand in hand with the 2 basic operations that I explained here: addition and scalar multiplication. Right? Anyway, just by looking at this, you can say whether it's linear or not. Now there's another one. It is R3. It takes any vector in R3 to another vector in R3. Here it is again the same. But which of them are linear? Okay, you can just by looking at a linear transformation, you can say whether it's linear or not. How? What's linear? Linearity. Linearity is the following. I mean, linear means what? You take variables, you combine them using what? Using the very basic operations you have learnt when you are like this size, when you are in grade 1 and grade 2. What are the very basic operations you have learnt? Addition, right? Subtraction is the opposite of that. So addition covers everything, addition. And what's the second thing? Scalar multiplication. You haven't learnt how to multiply x and y when you are in your grade 2 or grade 3. But you learnt 2 times 3, 5 times 6, 2 times 5, stuff like that. So it's a multiplication by a number, right? Look, this is a multiplication by a number. Multiplication of vector, a vector multiplied by a number, right? Multiplication of a vector by a number. This is addition of 2 vectors. Simple. There you add numbers, right? So addition and multiplication, scalar multiplication, are used to come up with linear expressions. If the right hand side has the expressions which are all linear, all should be linear, everything should be linear in there, then the transformation is linear. Simple, right? Is it linear? So always you have to, it should be like this: ax plus by plus cz. That's the linear expression of ax, y and z. Ax plus by plus cz, like that. If you plug in xy, x is equal to 0, y is equal to 0, z is equal to 0, you should get 0. Is this linear? Yes. Why? They are added, and before that they are scalar multiplied, like 2x1, 3x2. Is this linear? No. Why not? This is linear, but this is not. If you plug in 0 for this, it will be 4. It's not linear because there's no variable here. If you add something like that, it's a shift. It's not linear. It should be like a is ax plus by plus cz. If you add d, then it's not linear, right? So this is not linear because of this. Not linear. What about this one? This is linear because they are combined using addition and scalar multiplication. Here it is multiplied by 1, 7 and 4. This is linear. Multiplied by 6, minus 4 and 3. What about this? This is not linear. x1 and x2 are multiplied. It's not linear. What about this one? It's linear. Everything is linear in there. In fact, you can write this. When it is linear, you can do it like this. You can play the game like this. I can write this as a product of 2 matrices where the right hand side is the same as this one. Sometimes right hand side is a part of that. But if you are in the same dimension, then right hand side is exactly the same vector. So how do you write this? 3x1, 1x2, there's no x3. But here it is 1x1, 2x2, 1x3. It is defined using the matrix multiplication, right? Here it is like this. Now look, applying the transformation is equal to the multiplication of a vector. Sorry, multiplication by a matrix. So this is called what? Matrix of linear transformation. This transformation is linear, right? I forgot to write linear. So this is called matrix of linear transformation or matrix of T. T is linear. If it is not linear, T is a linear transformation. If it is linear, you can always write it like, represent it using a matrix. But here you cannot. You cannot write it as a product like that. That's the only thing you need to know in linear transformations. If here, because of this is the transformation is not linear. If you try to write it like this, you cannot. Because of this 4. If you delete this 4, you can. Again, if you delete this part, you can write it as a product of two matrices, where the right hand side you get x1, x2, x3. This is all what you need to know, right? So if it is linear, you can see that it's linear. Then this you can write it as a product of two matrices, and this is called the matrix of linear transformation. Why do you do that? Why do you call it like that? Because rather than applying this one, you can simply multiply it by this matrix. If it is A, Tx is Ax. Simple, right? You can write it, if you write this vector as x, right? You can write it like this, where A is the matrix of T. Right? Okay, right. Now, there's another thing we need to pay attention to. But before that, I need some space. Therefore, I have to erase this one. Okay. Now we can come up with this one. If it is possible to write a matrix like this, then you can show that. You can show the following. Hold on. You have this one. You choose two vectors. Now the first statement is for addition. I told you. It should preserve the very basic operations, mathematical operations you learnt when you were in your grade 1 and grade 2. That's all. That's what meant by the linearity. Addition should be preserved. That means, can you remember a place where you have used this one? At least we have used this 3 times before coming to this place. Where? When you differentiate, when you have two functions, you take one at a time. Like, how would you differentiate x squared plus sin x? You apply like one at a time and get the sum. The derivative of x squared is 2x, derivative of sin x is cos x. You write it as 2x plus cos x. With sigma notation, you have used the same thing. With integration, you have used the same thing, because those operators are linear, right? Second, this is the preservation of addition. This is the preservation of scalar multiplication. Have you used this one? Some places. At least we have used those in 3 different places. Think about this, right? I can give you an example. For the first one, like say differentiation, right? This is a linear operator. That's why you can, you have used it like this. You do it like this, right? Okay. Haven't you used it like this? If you have a constant in front, you can pull it out. That's called linearity. Because when you have a constant, you can pull it out. Because it's linear. Right? Another example. I don't have to put R here, right? Can you write it like this? You can break this into 2 parts. Why? Because it's linear. Similarly, if you have something like this, you can write it like this because it is linear. You can pull out that constant. Similarly, you can do it with integration because they are linear. That's all what you need to know, right? What are the operations? Addition and scalar multiplication. Look, addition and scalar multiplication. You don't need those 10 statements there, right? Okay. So, these are some examples for linear transformations. Now, we'll see something more interesting. That is part C. Right? I'll just take one example here. I wanted to do 2 examples, but this guy has eaten up this space. Therefore, I'll reduce number of examples here. Let's take this one. We know the matrix of transformation. Okay. Now, how do you write this? Okay, it's linear. You just by looking at this, you can say that it's linear. If you want, you can prove these 2, but it's not necessary. And here, you have to say that U and V are from Rn, and alpha is a real constant and stuff like that. I didn't write that. You know that you need to specify those 2. Now, it's linear, right? Because of that, you can write it like this. 3, we have done this one earlier. So this is A. Let this be A. A is the matrix of linear transformation. Therefore, like any linear transformation has a corresponding matrix, and any matrix has a corresponding linear transformation. Simple, right? Clear. Now, let's take some special vectors and see what happens, right? Now, we don't have to, we can drop this one here after, because why? Tx is this one. So, I will write it like this. Tx, x is this vector. Right? That's called matrix of linear transformation. Now we'll see some magic. Okay? Hold on. I have space there, so I'll. Let V1. Oh, UVW, let's take UVW, right? U is this vector. 1, how would I say, okay, 1, 1, 1. V, I would say 1, 0, like this, huh? Minus 1, 0, 1. W. One, minus 2, 1. Right? Then, I will take AU. What would you get if you multiply, if you perform the multiplication? 1 times 3, 3 plus 4, 3 plus 1, 4. 1, 2, 1, 4. 4. Now you can pull out 4. So now, look, here we saw that multiplication, like applying a linear transformation, is the same as a multiplication by a pre-multiplication by a matrix. Now, it's even simpler. Pre-multiplication by a matrix is equal to what? Multiplication by a number. Easy. So, in that event, the whole transformation can be represented by just a number. Right? Because look, Tx is 4x. Simple. Right? Let's take this one. AV. Minus 1, 0, 1. What is it? Minus 1 goes on top of this, so minus 3, 0, so minus 3. Here minus 3, 0, 1. Oh, sorry, minus 1, 0, 1, so 0. Here 0, 0, 3. You can pull out 3. Minus 1, 0, 1. Again, look. Here you need to multiply it by 3. You get the same vector. I mean, multiplication by a matrix is multiplication by a number. They are equivalent. Now, finally, AW. This is something very interesting, like linear algebra, but probably you haven't seen it like that. Okay, let's multiply. I'll perform the multiplication. Huh? If you do that, you get the same thing. Here, even special. Applying the transformation is equivalent to what? Pre-multiplication by a matrix is equivalent to multiplication by 1. Now, what are these numbers? What are the sum of those numbers? 4, 3 and 1. What is the sum? 4 plus 3 plus 1, 8. What is the sum of these diagonal elements? 3 plus 2 plus 3, 8. What is the determinant? This determinant. It is in fact 12. If you multiply these three numbers, you get 12. So there are some connections like that. Now, that means what? There are some special numbers like this, and there are some special vectors like this. If I combine all those, I'll represent these guys, x. This is just a number. Right? You don't have so many vectors, right? If it is 3 by 3, we have at most 3 vectors like that. If it is 2 by 2, you have at most 2 such vectors. Right? If it is 4 by 4, you have at most 4 such vectors. In fact, if it is symmetric, the symmetric matrix, this provides a basis for you, but those are some stuff that you need to learn in some other subject. But look, here if you represent this vector by x and this number by lambda, you can write it like this. Lambda is called the eigenvector, eigenvalue. Because here look what happens is, if you take any other vector, it will be rotated. Use any other vector and see, like I don't have enough space like to write that. Like if you take 1, 1, 2, for example, you get some other vector, weird vector. But here, their directions are not changed, right? But their what? Their length is multiplied. That's all what happened. Directions are, they were not rotated, but their magnitudes are changed. Here length is multiplied by 4. Here length is multiplied by 3. Here the length is multiplied by 1. If you substitute, if you take any other vector in these places, it will be rotated. And direction will be changed as well as the magnitude. But here, the directions are invariant. Right? So, lambda is the eigenvector. Eigenvalue. What's meant by the eigenvalue? Eigen is a German word for characteristic. Right? This is a characteristic value. But there's no space in between. So, it's a characteristic value. Means what? If you take those special vectors, when you apply this transformation, they are multiplied by this scalar, like they are multiplied by a scalar. Those scalar values are called eigenvalues. What is x? They are called the eigenvector or the characteristic vector. This is a German word for characteristics. So x is an eigenvector. Why do you call them as eigenvectors and eigenvalues? Because using those vectors, you can characterize this operator. Right? Like you can characterize people like that, right? For example, like if you take some, summary and summary. You know how you can characterize them. You know what they do. How do they look like? What kind of programs they do. If you take Nadia Gurge, a different guy, he does a different thing, right? If you take Tharupati Vijay, the actor, you immediately identify him as an actor who can fight simultaneously with probably 100 people, right? Likewise, if you take Bruce Lee, you can characterize him in a certain way. Likewise, this is a very basic way of characterizing this operator, or the linear transformation. Using these eigenvalues and eigenvectors, you can simply characterize, you can explain everything about this transformation T. That's why they are called eigenvalues and eigenvectors. I think the German mathematician has come up with this idea. That's why they were called like this. So, there are enormous applications of these guys. Eigenvalues and eigenvectors. Let's see one of them later. Now, this is a definition. You know what it is. Like, if A is a square matrix and if this is so, it means this one. Then lambda is called an eigenvalue, where x is called the corresponding eigenvector. How do you find them? You go for this, bring this down to the left hand side, multiply it by I to make them conform. I mean, like introduce the conformity between this addition or subtraction. Then you can pull out x. The ODE of I should be the same as the ODE of A. Now you have this one. Now, how do you find lambda? Now, you can plug in 0 for x, 0, 0, 0. It works, right? Put 0, 0, 0, what happens? Answer will be 0, 0, 0. You can get the same value. So the trivial solution, that's called the trivial solution, useless solution. That will be a solution to this. But you need to come up with some useful solution. That's called non-trivial. Trivial means useless. Trivial means like, say, sometimes people say, here we don't use it much. Say somebody is worrying about a certain girl with whom he has broken up, right? The relationship. The other friends say, oh, trivial thing, don't worry, forget about it. Trivial, useless thing like that, trivial thing. Or something valueless, something useless. Doesn't have any value. That's called trivial, right? Here trivial means 0 values, all are zeros, right? So now think about, the right hand side is 0, are all zeros. Therefore think about this example. If you try to write it as a product, in the form of matrices, you will end up with this. 1, minus 1, 1, 1. You know the solution to this, right? One is x minus y is equal to 0. This one. Other is x plus y is equal to 0. So solution is right there. X is 0, y is 0. Trivial. Right? Now what about the other one? Let's come up with some other example. X plus 2y is equal to 0. There are two equations apparently, but both are the same. Both are the same. If you try to represent it using matrices, here you have 1, 2, 1, 2. If you try to find the solution graphically, x plus 2y, so it will be like this. Both lines go on top of each other. So everywhere is a solution. There are infinite solutions. It's called non-trivial solutions. Like for example, I take y is equal to t. If y is t, x is equal to minus 2t. If t is 1, you have 1 and minus 2. When t is 5, you get some other solution. Those are called non-trivial solutions. Has some values. Now look what happens. If you take the determinant of this, which is 1 plus 1, 2. Here, what is the determinant? It is 0. So non-trivial solutions, you need to have 0 determinant. For trivial solutions, you need to have non-zero determinant. Like those days when Indian Army was here, there was something like that. Because they have they send the troops who are really uneducated, right? So they say, okay, identity card. They ask for the identity card. Yes, identity card, no problem. No identity card, yes, problem. They say like that. So here it is something like that, right? For trivial solutions, you need to have non-zero. For non-trivial, you need to have 0. Like yes, identity card, no problem. Yes, no identity card, yes, problem. Like that, right? Okay. So here, this is the relationship between the determinant and this one. So here you need to have non-trivial solutions because you don't need zeros. You need to have some useful values. So for non-trivial solutions, that means for these type of solutions, you need to have 0 determinant. Then you take it as 0. Then you find lambda using this. Then you use that lambda here, you plug in lambda there, and you find x. You know how to do that. But that's how you do it. That's the meaning of eigenvalues. Now we'll see one practical example that is encountered in civil engineering anyway, but I'll do it. All of you can understand it. Okay. So after this we'll go through that example. Then I'll show you the connection between the eigenvalues and differential equations. Okay, thank you.